Welcome to this video tutorial on the conservation of momentum. Let's begin by defining momentum, which typically is called P. The momentum of an object P is equal to the mass of the object multiplied by its speed, v. We can also write this with vector notation, so that the momentum vector is equal to the mass multiplied by the velocity. Therefore, if we did a small example where we had a ball with a mass 5 kilograms and a speed of 5 meters per second, then P will be equal to 5 for the mass multiplied by 5 for the speed, which is 25. Well, what are the units? Well, as you can see, momentum is equal to a mass, which has the units kilograms, multiplied by speed, which has the units meters per second. Which means that our momentum is 25 kilogram meters per second. If you're ever in doubt about the units of a variable, you can always do this method here, which is called dimensional analysis. So what if we have multiple objects? Let's say balls A, B, and C. And we wanted to find the total momentum. Well, in this case, whether we're working with vectors or scalars, we simply add them up. If we define the total momentum to be pt as a vector, then this will be equal to pa plus pb plus pc. This is very simple with vectors. Note that this is slightly more difficult when it comes to scalars. The important thing about vectors is that the information about the direction of the momentum is kept. However, if we had one ball A heading to the right and one ball C heading to the left, then their momentum scalars could be equal. However, they'd be acting in the opposite direction, meaning that adding them together would give a large momentum value, when in truth, when considering vectors, you would see that the momentum C would be heading in the opposite direction to momentum A, and so they would in fact cancel out. Therefore, when working with addition in momentum, it's probably best to use vectors, or be at least certain with the direction of your scalars. Lastly, we have the conservation of momentum. If we consider two times, time 1 and time 2, where time 1 is before a reaction and time 2 is after a reaction, so we'll say after and before. Before a reaction, we may have two balls heading towards each other, where this might be ball A and this might be ball B. And then after the balls have collided and now are heading back the opposite directions, this is A and this is B. For every situation that we will be considering, we can say that the total momentum is conserved, and therefore we can say that pt1 is equal to pt2. This means that the total momentum before and after the reaction is exactly the same, meaning that we can then write that pa1 plus pb1 is equal to pa2 plus pb2. And we could also sub the masses in and then get our velocities too. Welcome to the example part of the tutorial. Here you will see a ball sitting on the top of a rock on the exoplanet TRAPPIST-1d. the rover will knock the ball off of the rock and it will roll down, hitting another ball. Using the conservation of momentum, we're going to try and predict the final speed of the second ball, where the first ball is the one sitting on the rock at the beginning, and the second ball is the rock sitting on the ground at the beginning. From our conservation of momentum, we know that the total initial momentum is going to equal the total final momentum. In this question, we have two balls, and so therefore we can write this as the initial momentum being the initial momentum of ball 1 plus the initial momentum of ball 2, which will equal the total final momentum, which is the final momentum of ball 1 plus the final momentum of ball 2. We know that P equals mv, where v is a general speed. We're going to use this using scalars, because for this question we are assuming that all objects move in the same line. As you can see here, we've called the initial speeds u and the final speeds v. So therefore, when we write our initial momentum, we have m1u1 plus m2u2. These are the initial momentums, will equal the final momentums, and so we use the final v's for our speed. As you can see, we want to find out v2, and so we can rearrange this equation for v2, and if you take your time, you will find out that you get the following formula: m1u1 plus m2u2 minus m1v1 all divided by m2. And now this is a simple case of subbing in our values. v2 equals m1, which is 10 kilograms, times u1, which is 0.38, plus m2, which is 1 kilogram, multiplied by u2, which is 0, minus m1, which is once again 10 kilograms, multiplied by v1, which is 0.17 meters per second, and then all divided by m2, which is 1 kilogram. Therefore, if we sub this into our calculator, we will get 2.1 meters per second. Let's compare this to the correct answer, which is 0.28 meters per second. This is very different, and so we have to decide why. The reason is because in this question we assume that there is no energy loss. We assume that it is something called an elastic collision, when this is never going to be true in real life. And in this example, there is a huge energy loss to the environment. This could be through many different methods, such as heat or sound, and this is something that the conservation of momentum does not account for. And therefore, in the following questions, we'll have to be perfectly clear that our experiment will exist in these perfect conditions. As for dealing with elastic and inelastic collisions in the future, there will be video tutorials coming out soon about how to use more facts alongside with the conservation of momentum to solve more realistic problems. Let's move on to some examples which do exist under perfect conditions. Here we have two examples that have perfect conditions that allow us to use the conservation of momentum. Firstly, a projectile is launched into the air and it falls back down onto the ground, hitting 5 identical balls with a mass of 2 kilograms each. If the speed of the projectile is 5 meters per second and the mass is 20 kilograms, find the speed of each of the balls. And this is assuming that the momentum is shared equally and no momentum is lost to the surroundings. We start off by writing the initial momentum is equal to the final momentum. In this question we will use scalars, and we also know that the initial momentum is equal to the mass of the projectile, which I shall call big M, times the speed of the projectile, which I will call u. We know this is equal to the initial momentum because it falls back down onto 5 identical balls which are assumed to be stationary. This is then equal to the final momentum. We are assuming that the projectile falls to the floor and therefore comes to a stop, and then all its momentum is shared equally, meaning that we can say that the final momentum is equal to 5 times the final momentum p of one ball, in which the momentum of one ball shall be little m v, where v is the speed of a given ball and m is the mass of a given ball. Now we want to find the speed of each of the balls, meaning that we rearrange this equation for v, which will be mu divided by 5m. Then we sub in our values of 20 kilograms, 5 meters per second, 5 multiplied by small m of 2 kilograms. We can cancel out the 5's, leaving us with 20 divided by 2, which is 10 meters per second, which is the speed of each of the balls. Secondly, we have another example in which no energy is lost to the surroundings, and now we are working with vectors. We can see that two objects collide, object 1 and object 2, and we need to find m2 and v2. Let's start off by writing down that our initial momentum is equal to our final momentum as vectors, and then, as an extension, if we know that our initial velocity is u and our final velocities are v, then we can say that m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. And this is our conservation of momentum equation. As you can see, our v1 and our u2 vectors are null vectors, and therefore these terms will go to 0 or to null, and so therefore we can cross them out. This leaves us with m1 u1 equals m2 v2. Let's sub in what we know about these. We know that m1 is 5, that u1 is 2x hat plus 4y hat plus 2z hat. And we know that this is equal to m2, which we do not know, multiplied by v2, which we have up here. And now we need to find m2 and v2. This may not seem too obvious at first, but we've been told one more bit of information, which is that vx, which is our variable here, is equal to 1 meters per second. This means if we compare the x hat components of our two momentums, we can see that 5 times 2 in the x hat direction must be equal to m2 times vx, which is 1. This means that m2 must equal 10 kilograms in order for the x components to match up, which they must do in a vector equation for conservation of momentum. Once we know this, we can sub m2 and vx back into our equation, and we can expand out the brackets, meaning that we get 10x hat plus 20y hat plus 10z hat equals, if m2 is 10 and vx is 1, that is 10x hat, and so you can see these two do in fact match up, plus 10 times Vy y hat plus 10 times Vz z hat. By now comparing 20 y hat and 10 Vy y hat, you can see that for the two y hat components to be the same, Vy must equal 2 meters per second, and that for the z components to match up, 10 z hat must equal 10 Vz z hat, and so Vz must be 1 meter per second. And therefore, we can rewrite V2 to be equal to 10 times Vxx hat plus Vyy hat plus Vz hat, which is 10 x hat plus 20 y hat plus 10 z hat meters per second. Thank you for watching this video tutorial. Visit my website coherentphysics.com for many examples with fully worked solutions.